All right, let's get started. So this tutorial, so the projects in this tutorial is pretty fun because you can use the basic 3 board to display something on the monitor. And I didn't check. If you look at the monitor on your computer, are these VGA ports or HDMI? Hopefully it's VGA. VGA? Great. So I think what you can do is keep the terminal plugged into the monitor there and unplug the VGA port from the desktop, from the box, and plug into your basic 3 board. That's what I'm thinking what you can do. I didn't purchase 20 VGA cables for you guys. So no? Oh, it's wait. You have a VGA cable? So it's HDMI. It used to be VGA. You don't need it now. If you have it at home, you can try to grab it or do the experiments at home. So I'm going to give you a really quick introduction to some of the critical parts in the code. So first, the VGA has several standard protocols, and you can definitely find out these protocols over here in this link. So the most common one is a 640 by 480 pixels, and it's using a 25.175 megahertz clock. So this is a speed for each pixel. So everything I'm saying here is important. I mean, if you don't get it, you can come back to the recorded video. It's helping you to understand what's going on. Okay, if you don't get it, make sure you rewatch the video afterwards. Okay, first, one thing is important here is the pixel, just assigning each pixel on the monitor, right? So that frequency is 25.175 megahertz. Keep in mind, because you are going to create a clock divider over here. We're not definitely creating exactly 25.175 megahertz clock, but I have to convert the 100 megahertz clock from the board to 25 megahertz, which will work for this case as well. What I mean? So you can definitely do it in Verilog, but in this example, I'm introducing a different method for you, which is new, is to use IP block. So you can create a block, a chip, which is a clock divider, which receives a 100 megahertz clock and divide it by 4 times, so you are getting 25 megahertz. So you don't have to code it up by yourself. If you do the IP block, it's going to generate that chip for you. You just instantiate it in the test bench, which is actually easier. Okay, and so for example, if you are not using the IP block and you have to divide the 100 megahertz clock by 4 times, so you are getting 25 megahertz, how would you do that? A counter, right? So count it to where? To 4, right? So count it to 4 and then clear it. So you are getting the 25 megahertz clock. But anyway, just follow the tutorial. It's just generating an IP block, and you can directly use that output from the block to feed it into the Vga controller. And you are going to program code up the Vga controller and also the ROM. And the ROM is going to hold the data. It's a very similar task as you have done in the last tutorial. So you create a ROM, And the ROM has an address pin, and it doesn't have a clock. So whenever the address here changes, it's going to change the data output over here. And the data file is the image file, and you can download from here. It's nothing but a basis 3 picture. You look at this demonstration video, it's connecting the VGA port to the monitor. You can see the little picture is shown on the monitor. And it's very small because the VGA board is not that powerful. If you have a huge picture, sometimes it can be, the scanning rate can be low. So if you want to see a really steady picture, just use a smaller one. So here's an example of it, right? And there are some tasks for you to just display a solid color on the monitor, and also change the color of the monitor at a 1 hertz speed. Okay, these are the tasks for this tutorial. And now let's take a look at the Vga protocol. So what's going on and what's happening here? All right. So like I said, 640 by 480 is the most common standard protocol for the VGA communications. There are many others, but we are going to use the most common one. And if you get into this website, you can look into details. So I have some snapshots on my tutorial. So what are these parameters? And these are important, and to use these parameters in your Verilog. So first, look at the standard, this standard of the VGA display. It's 640 by 480. That's for the picture only at 60 hertz. So it's refreshing these many pixels at 60 hertz. All right, that's what's happening for this protocol. So it's 60 hertz for refreshing these many pixels, and the vertical refresh will be this many hertz. How this is calculated. So first we have to know how many pixels in a vertically and how many pixels horizontally. This is a little bit confusing, right? So the pixels, the active pixels area is actually 640 by 480, so it's wider. Okay, so the width is larger than the length. It's very common for all the monitors. This is wider compared to the height. Okay, so 640 for the width and 480 for the length. But it's just for the active pixels. However, when you are scanning all the pixels on the monitor, it's actually more. There are actually more pixels to be assigned, because you need, some of the pixels is called front porch, the sync pulse, the back porch. I'm going to show you what are they really quickly, and the whole line. So you are looking at the whole line. So for a 640 by 480 VGA protocol, it actually has 800 pixels horizontally and 525 pixels vertically. All right, that's the protocol. Just need to know there are 800 pixels horizontally and 525 pixels vertically. And here, let's verify some of the numbers over here. This is a snapshot from the website. Okay, so 25.175 megahertz is the frequency for what? For every pixel. It's assigning every pixel at that speed. All right. How many pixels do you have for every row? 800. Okay. So the time it takes to scan the one row, the 800 pixels, will be 800 times 1 over 25.175 megahertz. Okay, does that make sense? And then this is the time it takes to scan one row for this VGA standard, which is this many hertz. If you compare to here, it's vertical refresh. whatever how it names it. But so this is the frequency of scanning every single row. Okay. And if you use the total number of pixels, which is 800 times 525, because 800 is the number of pixels for each row, and 525 is the number of pixels for each column. So 800 times 525 will be the total number of pixels for this VGA standard, okay? And that's, so 1 over this will be the time for each pixel, and this is the total number of pixels, all right? So this times this will be the time it takes to scan the whole page, the whole frame, which is this long. And you do 1 over this number, you are getting 59.99 hertz, which is very similar to 60 hertz. Okay, so this is accurate. So all the numbers are validated. And here is for the time assigned for the front porch duration. I'm going to show you what is that later. So that one has 16 pixels, and here's the frequency of for each pixel. So this times this, you are getting the time for the front porch duration, which is this number, 0.6355 microseconds. If you verify it in the table, it is correct. Right? This is how you understand the table and the numbers over here. So that's the timing diagram of the VGA port. Important, all right? Pay attention to this. So for example, this is the vertical scanning, all right? Vertical scanning. It starts from here, starts from the first active pixel. So these are the active pixels of the picture, all right? So the Vga protocol has the active pixels. How many of them vertically? One quick question. How many active pixels do we have for each column? 525? That's the entire number of pixels. But for the active pixels, it's only 480 because it's a 640 by 480 standard, right? So it's going to be 480 over here. And the front porch, so it just needed some buffering time over here after the active pixels, and the sync signal, which means it's going to tell the controller when it finishes the vertical scanning. It's working like this. So it scans all the pixels in one row and send the sync signal, which means the first row or whatever that row is done. And then it's going to be the second row. Okay? So that's a sync signal, or it's a row changing signal. And it's the same for the column changing signal as well. So let's still looking at this one. So these are the active pixels, and there's a little buffering time duration, and you can find out how many pixels are here for the front porch. So this is a vertical display area, right? So vertical display area, then we are looking at the vertical timing here, and the front porch has 10 pixels, 10 pixels. If you know there are 10 pixels to be assigned, then you know how long it's going to take, because you know how long it takes for each pixel assignment, right? So 1 over this frequency, all right? So one column is from the first active pixel until the end of the back porch. Okay, that's a entire column. So yes. So this is one period, right? From here to here. That's one period, because you can see that here's the back porch again. So it has to end here. It's going to start a front porch afterwards, but it didn't show it over here. Right. The same for the horizontal display area as well. How many for the horizontal? How many here for the active pixels? 640, right? 640. And for the entire row, 800. And now is the controller. S, Y, X, X are the active pixels inside the active pixel area. Because the picture definitely is not 640 by 480, it's smaller. So when you are looking at the Vga Controller Module over here, I have X, Y, X, X as the inputs. So the test bench actually assigns the X and Y dimension of the picture. It's smaller. You don't have to display everything on the 640 by 480 picture, right? You can, if you look at this example, it only displays a little basis 3 board in the corner. Right? It's only a little picture in the corner. Okay, and so this example is just telling you that you can define any arbitrary X and Y dimensions for your display. But this one has 80 by 80. And here's a module. I'm going to explain everything here really quick. So we are using definitely the horizontal display has 640 pixels. The vertical display has 480 pixels. And HFP, which is a horizontal front porch, that's that duration, which has 16 pixels. And the pulse width has 96 pixels. What's the pulse width? Which is the sync pulse. Okay, if you look at the table, so the sync pulse for the horizontal timing has 96 pixels. So the picture here is not drawn in scale because the sync definitely is wider than the front porch, right? Okay, so let's come back to the code over here. So just use the numbers from the tables, all right? Front porch is 16 for the horizontal display, and the pulse width for the sync signal is 96, and the H limitation is 800. That's the max number for the horizontal display, 800 pixels. And the same for the vertical display, but I have 525 pixels instead of 800 for the vertical for each column. H count, V count, they are just counters. When you are counting for the each pixel, when it reaches any limitation, it's going to take a different action. So you need the counters over here. And enable, disable. So there's no disable, it's just enable 1 or 0. Whenever enable is 1, it's going to take some action. Whenever enable 0, it won't do anything. It's just like a flag. All right. So always the pulse edge is not the clock from the 100 megahertz from the board. It's a 25 megahertz clock divided by the IP block you are going to use. Just follow the tutorial to create that IP block, which is the clock divider. So when the H count is smaller than the limitation, the horizontal limitation, so the counter should add 1 to itself. It's not reaching 800 yet, just keep adding, right? No problem with that. Otherwise, if otherwise, whenever it reaches that limit, then reset it back to 0. All right. And if the vertical count is not reaching the vertical limit yet, adding 1 to itself. Otherwise, just reset to 0. It's just like keep scanning to here. If it's reaching 800, then reset. Otherwise, just keep adding. Right. So that's the overall counter setup. It's because you can see all the other modules or conditional statements are independent to each other. So whenever this conditional statement is being satisfied, then it's going to execute all the statements inside. So you have if something, if something, if something, if something. These are just all the multiple inputs to a multiplexer. You can see like whenever one of them are satisfied or multiple of them are satisfied, they are going to execute one of them or all of them. They are independent from each other. Okay. So we just explained the first conditional statement. What about the second one? So the first one is valid because whenever it not reaching the 800 yet, keep adding 1 to itself. Otherwise, just reset it to 0. But also during that assignment or checking, you also want to check if it's beyond that active pixel area yet. So X, Y, and XX, these are the dimensions of the real picture you want to use. You assign them from the test bench. Right? So it looks like this. So here is the entire, that's the entire monitor, right? We use that mouse. That's the monitor, which is 800 by 525. And here is the SY by XX. Here's SY, here's SX. Okay, definitely scanning all the 800 pixels, but also whenever it's beyond this boundary over here, you don't have to do anything. You just want to disable the display because it's not showing anything anymore. And you don't have active pixels after that. So if the V count is larger than SY, just assigning a not an invalid address like -1 to this one, you can assign any invalid number to it. So you're not taking out any data from the pixel from the ROM and disable it. So enable becomes 1, becomes 0. Else, if it's not reaching the SY yet, then you want to check if it's reaching SX yet or not. So if this is larger than that, then do this else, right? So under else, which means V count is smaller than SY, so it's still within the max vertical count. And you want to check if this is smaller than this. If it is, then enable it because it's within X, Y, and XX, that limitation. And definitely add a 1 to the address. This is taking out another data from the ROM, the next data from the ROM. Otherwise, just disable it. It's all outside of the XYX area. So these ones will give you an enable 0 or enable 1. And then you can check enable afterwards, right? So if enable is 1, which means it's within the XYXX area, then because the pixel data has been received by these data bus, so send pixel data from bit 0 to bit 2, there is a 3-bit data to red. I'm going to show you really quick why is that. And so it's an 8-bit, you can see it's from bit 0 to bit 7. So it's an 8-bit data for the image. And separating the 8 bits into bit 0 to bit 2. So it's 3 bits for red, and 3 bits for green, and 2 bits for blue. That's how these bits are being assigned for different colors. And otherwise, just send zeros to all of them. But I can see that I didn't put a 3 bits over here, but I think you should do a 3' B000 because the 8 bits are being separated as 332, not 322. But anyway, it's just a 0. So 2 bits, 3 bits are both zeros. This is not affecting results. all right? So if the H count is larger than this and H count is smaller than this, send it to the sync H, so the horizontal sync signal to 0. And now let's see if this is making sense. So H display, what is that? 640. HFP, it's a horizontal front porch, 16. HPW, which is a horizontal pulse width, which is a number of pixels for the sync, right? When H count is larger than this, but smaller than this, now let's come back to the timing diagram. See, when it's larger than this, which means it's larger than this, it's on the right-hand side of after this line. But smaller than this, which means it's within this area, right, within this time duration, you should pull the sync signal to 0 to indicate that the row scanning is completed. Otherwise, you just pull it up to 1. See, all the rest of the timing diagrams, the sync signal are ones, but only during this time frame, it's a 0. So that's how you implement that timing diagram into a Verilog code. Now let's come back here and take a look at that again. So whenever it's larger than this, but smaller than this, you know, makes sense. You want to see a voltage low, just pull it down to ground. Okay. Otherwise, pull it up to logic 1. Same for the vertical sync signal. It's very similar. You just want to change the variables over here. So that's everything for to implement the timing diagram for the Vga protocol 640 by 480. So that's the Vga module. And here is the test bench. See what we need in the test bench. Definitely, you know, the X and SY parameters can be changed. So that's why you want to use them as inputs. So you can change it in the test bench later. And because everything will be implemented on the IPGA board, so there must be ports on the board for the VGA connection. So we want to take a look at the constraint file. So I'm opening up this guy. And you can see that if you scroll down, you'll be able to see the VGA connector. So there are ports and names for the VGA connections. So by looking at that, can you tell me how many bits are there for each color? It's RGB, right? So VGA is RGB protocol. So how many bits are there for each color? 4. Okay, so how many bits do you have totally for all the 3 colors? 12. But how many bits did we use in the Verilog script? 8. Okay, so does that matter? I mean, can we still display the picture? Yes, we can, because that's what you saw on the YouTube demonstration, right? So we can still do it. So what's the consequence of reducing the bits, number of bits for each color? So totally you can use 12 bits, right? But we are not using all the 12 bits. We only use 8 bits. Then we are doing like 3, 3, 2, right? 3 for red, 3 for green, 2 for blue. So which means that, you know, we're reducing the number of bits, which means it's not resolving all the color changes. So we're eventually getting some skew on the display. So that's when we're looking at the basis 3 picture over here. So see, the basis 3 board is blue, right, on the PCB. If you look at this guy, is that totally, it's not reflecting the true color of the basis 3 board, right? Because we don't have 12 bits for each color. Only 2 bits for blue. So how many different colors you can show in blue? 4. Only 2 bits, right? So you have 4 bits, you have 16 different levels for that to show that the subtle changes in the color. But now we only have 2 bits, actually 4. Yeah, 4 different levels for that color. So it's not reflecting the true color of the picture. Okay, so you just want to let you know what's happening over here. Okay. Now look at the constraint file. For the VGA section, except for the color bits, what else do we have over here on the board? The sync signal, okay? The H sync and V sync, right? And that's it. 12 bits of colors and 2 bits for the sync signal. So we are designing the Vga controller and the test bench. Here's a circuit diagram. So Vga controller receives SX and SY signal. It's a dimension for the picture from the test bench. So you need 2 wires here. And you need a clock divider dividing the 100 megahertz to 25 megahertz. And the Vga controller does need it because pass edge 25. Okay. And need a ROM to store the image file. And it has a 13 bits for the address and 8 bits for the data. 8 bits for the data, not 12 bits. Keep in mind, 8 bits. And for the Vga controller, definitely after it takes the data from it, it's going to separate all the 8 bits into 332 and assign them to the ports, the RGB ports over here, and which are shorted to the physical port, VGA port on the IPGA board. 332, all right, keep in mind. And also the H sync and V sync. These are signals you created in the VGA module here, because they are here, right? H sync being put down to the ground, and then up to the VDD. So you can form that pulse, and that pulse is being sent to the test bench over here. Okay. In the test bench, instantiate the clock, the 25 megahertz clock, and also instantiate the memory, the ROM, and also the VGA module. So you have these 3 modules in the test bench, 1, 2, 3, with connections, and can repeat what I did in the tutorial. Fortunately, the entire script here and here, these are provided. If you just code it up in your Vivado and make the connections, you have a VGA port connected to the monitor, it should work, okay? You should be able to repeat this work. However, I also ask you to modify the code to show a solid color on the monitor and also show the different colors and being changed on the monitor for each second. So these are 2 new things which I didn't provide the script, but it can modify from the example code. Just let you know that in the RGB, it has a RGB code for each color, right? If you give, for example, 1111 to R and both zeros to G and B, you are getting a pure red color. It's a combination of the R and G and Bs. And there are 16 options for each color. So totally you have 16 times 16 times 16 combinations of all the colors. So it's really, I think it's enough, you know, it's definitely, I don't think your eye can resolve that many colors, but you do have the capability to make all the changes. Any other questions for this one? Nope. All right, a quick note for the lab this week. It's a 2-week lab, and I provided the example code and crossed out some of the sections in the code, but eventually I thought it's probably better to let you code out from the scratch because the example provided too much information in there. But you guys have 2 weeks to work on it, and so I think I'm going to do it this evening, which is I will provide an introduction video, a short lecture within 20 minutes. I'm going to post it on the top of the tutorial, to probably make it a little bit easier for you guys. And definitely refresh the browser. If you cannot see it by tomorrow, refresh the browser, and you don't have to come to the lab, but if you come over, I'll be there and help you, try to make it work. Right, just expect an introduction video on the top of the tutorial. Okay. Any other questions?